All right, coming to you live from study hall. Everybody say hello.
Hello.
See how excited they are? They're going to learn about this John along with you. You got 9th to 10th grade, some you mix and match, right? Head Start. You at home, they know Head Start. You got to know this stuff. All right, let's go. Math aside, force vectors and equilibrium. So let's go on this business. We did a bunch of vectors earlier this year. We did vectors back in Notes 2, Unit 2. We did them back in Unit 4. We had homework and skill drill associated with them. In fact, just to give you a little preview, I pulled some of these up. Way back in Unit 2, we first introduced how you're drawing your vectors here. And we talked about what they mean, they represent. We did some simple versions on here. And then we went over and we put them at an angle. We measured them with the scale. We talked about combining them head to tail, circle to start, X to finish, and drawing the resultant. And then we did a few simple cases of 0 degrees and 180 degrees. And we had Carl on the people mover at the airport, if you recall. So adding, subtracting, sometimes canceling out altogether. Okay, that was that. We then did these with a bit more detail in Unit 4. Here we talked about doing them at any angle. So again, circle to start, X to finish. Make them head to tail, draw that resultant from circle to X. That process is the same throughout. So no matter how funky the drawing becomes, the process is the same. We showed a couple of ways to go about actually making your resultant when you're at some other angle, some off angle from 0, 90, and 180. Generally, again, circle to start, X to finish. Or if you preferred, we had this graphical method here where you had to make a nice parallelogram. Repeat the sides, opposite sides are parallel and congruent, and that helped you draw them. Okay. We even went through the process of breaking them into components. Now, additionally, in Unit 4, we talked about, let's go back. Here we go. We talked about how to solve a big drawing, which you're going to see in the homework. So the blue arrows here were the original. I gave you 3 different versions of it. Scaled diagram method, which you just measure everything out real carefully. And you repeated the angles. So this angle and over here, you brought your protractor over. There's our protractor. Say we had that angle of roughly, what's that? This is the big angle. So there's 90, 100, 10, 20, 30, 146, something like that. You come over here and repeat that angle, 146. You can sketch these out. Go back to these notes if you want to look at it again. We also did a component method. And finally, we had the law of cosines and the law of sines for those of you who are more math inclined. Okay, anyway, let's get on to what we're doing next. So we're going to mess around with this a little bit more. Here's one of the scenarios we have. It's like a reverse scenario where we give you a component like A right here, and we give you the resultant like R right here, and we ask you, what is the other component down here? Is it choice 1B, choice 2B, or choice 3B? And the key idea here is recognizing that the components combine head to tail to form the resultant. The components are the long way, the resultant is the shortcut. So if you recognize what's going on here, you say, oh, A plus B has to equal R. Actually, in vector notation, you would write A plus B equals R. But what that actually means is you have to connect them head to tail. If these are all vectors, it does not mean 3 plus 4 equals 7. It actually means take A and bring it down over here. So connect A so it's head to tail with B. A is this long and points to the right. We do something like this. All right, if this is A and this is B, then the resultant would be circle to start, X to finish. That would be the resultant. Clearly, that does not match. Wrong. Hopefully, you can see immediately that this choice 2 is not going to work. We can put B first and then A. It doesn't matter. Here's A. So again, circle to start, X to finish. There is your resultant. Clearly, that does not match. So that's out. Finally, we look at choice 3. Oh, okay. Let's get our A and B head to tail, get the components connected head to tail. A is this long in this direction. And now we Circle the start, X the finish. For our resultant. Oh, we've got a match. Choice 3 is the right answer. You can do the same process with question 6, where you put your components together to form your resultant and see which one matches. You can go through that process, works out just fine. Another way to think about this one, actually, if you look back at what we've been doing, think about the second piece the way I said this. The first way I said is the components combine to form the resultant. The other way I said it was the components are the long way, the resultant is the shortcut. What does that mean? Well, if the components are the long way, like this is the long way, then the shortcut should start at the same place as the components start and end at the same place that the components end. The resultant actually connects tail with the open tail and head with the open head, as opposed to the combined head-tail. So if you like the way we did it on 5, do it that way on 6. But for some of you, you may want to recognize that, oh, wait a minute. A is here. That's going to be the long way. I know it starts here. I know the resultant must also start here because it's just a shortcut. And I know that the problem must end here because the resultant is the shortcut from start to finish. That means that B must take me from that half path to the end. That has to be B. And of course, there's your choice 1. So you could have done it like you did question 5 or like 6. Question 5 is more of a brute force. Question 6, the way I just showed it here, is more of a finesse. All right, reminder for equilibrium. We've talked about this a bunch lately. The forces are balanced. You can even add on here, you can sleep through it. Net force 0, acceleration 0, no change in motion. So constant velocity or at rest. Okay. Now, you will sometimes get a question like this. A 6 Newton and an 8 Newton force are acting on a box. So you can imagine the box. Maybe the 6 is this way and the 8 is this way. Or maybe the 6 is this way and the 8 is also this way. Or maybe the 6 is this way and the 8 is this way. Of course, you get unlimited choices here. But the question says, which of these could not produce equilibrium? Basically, which could not balance? The best way to think about these questions where they say, which force could not produce equilibrium? Or sometimes they ask the question, which force could produce equilibrium? It doesn't matter which way it's asked. Either way it's asked, the simplest way to answer this question, whether it could or could not produce equilibrium, is via a legal triangle. Now you learned in math class a legal triangle. Leg 1 plus leg 2 must be greater than or equal to leg 3, which of course is the long leg. So rather than writing leg 3, it's better off writing leg long. Now, generally speaking, actually that's perfect. Let's leave it just like that. Leg 1 plus leg 2 is greater than or equal to the long leg. Usually when you see a triangle, it's going to be greater than, not greater than or equal to, but this is technically a legal triangle definition. That's going to help you with these. So if you can just remember that a legal triangle equals equilibrium, and illegal triangle is not equilibrium. I suppose if you were forced to guess, you would probably assume that. So what do we mean by this? All right, we've got a 6 and we've got an 8. If we look at choice 1, we have a 1. So with these 3, we have a 1, a 6, and an 8. Can you make a legal triangle with a 1, a 6, and an 8? Well, you take leg 1, 1, plus leg 2, 6, has to be greater than or equal to the long leg, 8. Is that true? No, that is not true. And so what I would write if I were you, you could not have equilibrium here. That's this one. It's illegal. You would not get equilibrium. Well, the question actually says, which could not produce equilibrium? So we already got our answer. Let's check the other 3 just so we understand the process. This is a 2 with a 6 and an 8. 2 plus 6 greater than or equal to 8? Yes, you could have equilibrium, and that's not what we're looking for here. Next one. It's a 5, a 6, and an 8. 5 plus 6 greater than or equal to 8. Yes, it does. So we could have equilibrium here. And then finally, notice the 14 is our long leg. So you would have a 6 plus 8 has to be greater than or equal to 14. Yes, we could get equilibrium here too. So the legal triangle really straightens you out for any of these could or could not have equilibrium. All right, let's go on to the next page. This is the same business up here we just talked about. Same deal. Question 8. Which could be in equilibrium? So as soon as you see could be equilibrium, you say, oh, I want a legal triangle. That's what I'm looking for, a legal triangle. That's it. So legal triangle, let's see. Is 5 plus 7 greater than or equal to 13? No. No, 5 plus 7 is 12. So no, so you cannot have equilibrium here. We want equilibrium, so this is not the right answer. Next, 5, 7, 9. Two smaller legs, add them, greater than or equal to 9. Yes, this could give you equilibrium. And over here, 1, 5, 7, take the two smallers, add them up, are they greater than or equal to 7? No, this could not be equilibrium. Correct choice is 2. 9 is a nice question too. It's kind of a fun, it's almost like a fun little mini logic question right here. Two concurrent forces. Concurrent just means at the same time. Con is with in Spanish. Anybody know Italian? Nobody speak Italian in here? Nah. I think it's something like that in Italian too. But con in Spanish is with, and current is time. Like current events, current is now. So with time is concurrent. Concurrent forces just means they're happening at the same time. It does not mean they're pointing the same way. Concurrent forces have a max resultant of 40. Well, hopefully you remember to get a maximum resultant, what angle should these two point? Like this, like this, or like this? No, if you want a max resultant, they should point in the same direction. That's max resultant. That's a 0 degree case. Both arms point the same way. They are not separated at all in direction, 0 degrees. So that would be max. Minimum resultant would actually be the 180 case. That's where they oppose each other. You're going to end up subtracting. So here, they want to know. We want the max to come out to 40. And we want the min to come out to 10. So look at the choices. Just do it. Would 0 plus 40 give you 40? Yes. Would 0 minus 40 or 40 minus 0 give you 10? No, that's no good. Next one. Would 4 plus 10 give you 40? No, we're already out. Next one. Would 4, sorry, that was 4 plus 10. Would 4 plus 40 give you 40? No, we're already out. So finally, look at the last choice. Would 15 plus 25 give you 40? That's good. Would 15 and 25 subtracted give you 10? Yes, they would. There's your answer. Okay, good. Now, we have this new term. Sounds fancy, but actually it's exactly what it sounds like. And the term is equilibrant. Equilibrant. Don't worry about it. You're okay. Eat your heart pumping now again, right? Equilibrant. Equilibrant is the bringer of equilibrium. It is not the resultant. Be careful here. The equilibrant is the bringer of equilibrium. It balances the result. So if we went back a page here, you know, this was the resultant. What would balance it? Something going the other way of the same length. This is the resultant. What would balance it? Something going the other way of the same length. That is the equilibrant. Okay, that is the equilibrant. So we have 4 diagrams, and I want you to find the equilibrant. This is a beautiful review right here. Check this out. So we need to find the result. We need to find the equilibrant. First, we got to find the result. So step 1, circle the start. Oh, we got like both tails here. There's your start, X the finish. This is what you all should be doing. Well, there's a problem there. These are not head to tail. In fact, some people might be so inclined as to run over here and do some nonsense like this. Don't do that. This is right. and this is up. How could right and up combine to make either down right or up left? It can't. So that dashed line right there cannot possibly be correct. Don't get sloppy and just start slapping in hypotenuse for nothing. All right. So a start and two finishes, that's a problem. We got to move one of these. Let's pick one to move. Let's move the up. It is exactly this much up. I'm going to move over and still point it up and keep it the same length. Boom, there we go. That is our new circle to start, X to finish, and the resultant will be directly from the start to the finish. There it is. This one, of course, is also 10. And so you needed to get that length of resultant. The resultant here, of course, is just Pythagorean theorem. Square root of 10 squared plus 10 squared. Some of you already know that's a 10, 10, 10 root 2 triangle. So the resultant here comes out to about 14. You can do the math there. That's your resultant. But now you need an equilibrant. The equilibrant balances the resultant. The equilibrant goes the other way from the resultant. So if the resultant is 14 this way, the equilibrant is exactly 180 degrees the other way. Is your equilibrant 14 newtons. We can label up our resultant too, 14 newtons. Boom, there it is. Oh, let's check out the next one over here. 4 and 3. So if we circle the start, X the finish, one start, one finish, that's a good sign. This thing is already head to tail. In fact, if you look at left and up, we should result in left and up. And so in fact, you notice circle the start, X to finish, we do result in left and up. This one, of course, you could do Pythagorean theorem again. 4 squared plus 3 squared, but you could also recognize this as a 3, 4, 5 triangle. So this one actually is just 5 newtons. There's your result. Good to go. Up and left, as we expected. However, the equilibrant should balance this. Now, you don't have to draw the equilibrant starting at the tail, running the other way. You could draw it right next to it. You could do something like this. As long as you have the correct length and the correct direction, the equilibrant can be drawn right here. It doesn't matter. Correct length, correct direction. That's the key. How about this funny looking one down here? 25 newtons. Well, you may say, wait a minute, I don't know what, just follow the procedure. Circle the start on the exposed tail, X the finish on the exposed head. That's it. It is its own resultant. In fact, the resultant is exactly here. It's 25. So what's the equilibrant? The equilibrant can also be drawn head to head coming at it. It opposes it. It is exactly 25 newtons the other way. So you're welcome to do this. That would be fine too. And the very last one, right here, circle the start, X the finish, one start, one finish. That's a good sign. If you're not sure, this points up and right. So our result should be up and to the right. And as you see here, it is. Here's our resultant. Of course, you can do Pythagorean theorem to get this. What's that? 15 squared. That's 36 squared. But some of you might actually recognize this is a 5, 12, 13 triangle times 3. So this one actually comes out to 39 newtons. And the equilibrant will balance that. So we draw your resultant first. And you can even make it offset. It doesn't matter. What matters is it's the same length, opposite direction. Boom. There's your review. We'll do the homework on it. Check out real quick here. Anything worth discussing on homework. So here's the A, B, and R. Remember, A and B have to combine to give you the resultant. Here, it says find the equilibrant. Find the equilibrant. But of course, in order to find the equilibrant, you must first find the resultant and then go the other way. Down here, the force necessary to bring equilibrium. To bring equilibrium. Well, that is the equilibrant. But of course, to get the equilibrant, you must first find the resultant. All right, down here, 2 more questions with A. And you don't get a choice. You have to sketch or figure out what B would be to give you R. Remember that vector notation, A plus B equals R. If you think of these as the long way, and you think of this as the shortcut, that could help you visually put these in order and figure out what B would look like. All right, on the next page, equilibrium. Well, you know equilibrium means all the forces have to balance, so figure that out. Here's a couple more equilibrium questions over here. You'll be able to handle those no problem. Here, which force could not produce equilibrium? Not produce equilibrium means you want an illegal triangle. And here, which force could produce equilibrium? You want that legal triangle. Here's another one just like we did. Actually, just think this one through. As it changes from 0 to 180 degrees. So draw them at 0, and then draw them at 180. And you think about what the resultant will come out as. Here, which could be equilibrium? There's that legal triangle again. These explanation boxes are not here for my help. They're there for yours. And here's another one just like we did, the max and the min. And then down here, which vector represents the force that will produce equilibrium? Hopefully you know what that is by now and what you need to find first. The last question is this one. Oh, it's a dandy. So this one right here, you have to find, where is this? Determine the scale, construct a resultant, and then what is the magnitude and direction of the resultant? And how many degrees away from PA? PA is this one. P up through A, to the tip of A. And so you got a few options on this. Unit 4 is where we talked about the different ways you can sort this out, whether you're drawing it carefully, whether you're doing laws of cosines and sines, whether you break into components, whatever it is, just make sure you take care of this thing. Okay, good. Just in case you have the inability to print here, just in case you have the inability to print, you know, I'm going to check real quick. Actually, what I'll do for you, those of you with the inability to print, literally print page 3 right now and look at it and tell you the length of PA. By the way, there is a page 4 that just gets to talking about some advanced stuff. You know, you don't need to look at it. There's no requirement there, but you might find it interesting. So, PA, in case you don't have a printer for this, the angle there is measured, is marked 120 degrees, so you should have no problem with that. The PA, in my printer version, and you all can use this scale, or this measure, PA is, let's see here, 11.15 centimeters. So this 32 newtons, this length right here is 11.15 centimeters. If you actually printed it at home, your printer might scale it slightly differently, but let's make PA 11.15 centimeters, and you can use that then to figure out your scale and all the rest of this business. You can draw this out for yourself, by the way. You're completely capable of drawing this out for yourself. You have a protractor. In fact, I'll tell you PB also. PB. I'm going from the middle of that dot. PB. 6.75 centimeters. So PB 6.75 centimeters. I hope that coordinates. Should be close, if not exact. All right, that's that. Get to it.